So our work on permutations is going to focus a lot on arrangements and putting things in order, and we're going to do this a lot with a factorial. So for example, with the word special, notice that there are 7 letters in the word special, and we want to arrange all 7 letters. And we're only arranging the letters in the word special. So that's S, P, E, C, I, A, L. So let's pick. So for the first spot, we have 7 letters. And then if we use one, that's 6. And then if we use one, that's 5. And you get the idea. 4, 3, 2, 1. So essentially, instead of writing this like that, we could have just written it as 7 factorial. Okay, so that would have been an appropriate setup for problem 3, part A. And that's because the word special has all unique letters. None of the letters repeat. So we look at the same idea here with these problems. 4, F-O-U-R, that would be 4 factorial, would be how many ways to arrange all the letters. Which means technically there would be 24 ways. You would be invited to, if you'd like, you could go ahead and list all of them. See if you could exhaust all 24 possible arrangements. But again, I want to point out that the word 4 has 4 unique letters, because when we look at part C, you have N-O-N-E, 2 letters repeat. So if we were to make a list of all the letters in the word none, but I were to switch these 2 around, I still get the word none. So the problem is we're double counting. This is no longer an accurate count. So I can't just say 4 factorial like I did with part B, because part B didn't have any repeats. Part C has repeats. And if I start rearranging things with the word none, I'm going to get some repeats. So here's what we do. How many repeats do I have? I have 2 n's. So I divide by the repeats. And this would be the appropriate setup for part C. We could, of course, if you want to go ahead and write it all out, and then cancel things out, you would note that there's only 12 unique possible ways to arrange all 4 letters of the word none. So that's half the amount that we had for part B, where all the letters were unique. So that's pretty fascinating, that we would have double counted twice as much if we hadn't done the math right. Part D, well, I have 1, 2, 3, 4, 5 letters. And how many of them repeat? I have a 2 factorial there. So for books, that's how many arrangements there would be that would be unique. Good golly, bookkeeper, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 factorial. That's the total possible arrangements of all the letters, including repeats. But we have 1, 2 O's, 2 K's, and 1, 2, 3 E's. And so this would be the appropriate setup for part E. Convince yourself that for the word Mississippi, this is the amount of possible ways to arrange all of the letters in the word Mississippi. You might want to use some more to describe where some of these numbers came from. Now, for everything up to this point for this problem 3, we've been using all of the letters. So let's return back to the word special, where there's no repeats. And how many ways can we arrange only 4 letters at a time? So any 4 of the letters in the word special. So we only have 4 blanks this time. Now we can use any of the letters in the word special. That's 7. But once I use a letter, I can't use any more. And then this is what our setup looks like. So problems like G end up actually being a special type of problem called a permutation. And when we do a lot of counting principles, we're usually doing either permutations or combinations, and sneak peek, we're going to do combinations in the near future. But for now, let's focus on the permutation. So if I have an n amount of things and I want to pick r amount out of it and arrange them and put them in order, this is called a permutation. So permutation are going to be problems that have the words ordering or arrangement. So for example, this horrible looking thing is not much more different than what we did earlier in the previous video. So that formula will end up setting up like E pretty much. So how does this weird looking formula work? Well, it's saying, okay, first of all, n is always going to be greater than or equal to r. In other words, n is the total number of things you have, and r is the special amount you're going to choose. So for example, if we do part G again, we had 7 letters to choose from, but we were going to choose 4. So this would look like 7P4 for us. And then I would just plug it into this formula. So anywhere there's this n, I would put a 7, so it's 7 factorial. And then 7 minus 4 factorial. So again, if we're doing G again, there's a total of 7, right? Total of 7. And we're going to be picking 4-letter words. So that's a special amount that we're picking. And notice what happens if we simplify this, right? Well, 7 minus 4 is 3, so that's 3 factorial. So it's 3 times 2 times 1. And notice that the 3's and the 2's and the 1's cancel out. And I'm left with 7 times 6 times 5 times 4, which is what we did over here anyway in the first place. So that's how this works out. The permutations, it lets you set up a formula. If you don't want to think, you could just use this formula. As long as in the total that you've been given, and then how much a special amount that you're going to pick. And this is true if you're going to be doing arrangements, okay, or if you're ordering things. And when I mean ordering, it's like we're ordering a meal at a restaurant. Ordering means I'm going to put things in order, like lining up kids in line in order at the playground. Problem 4. How many ways can we select a president, a vice president, and secretary? So that's 3 positions from a group of 5 people. So this looks like 5 total. We're choosing 3 special positions. This is 5 factorial over 5 minus 3 factorial. That's 5 factorial over 2 factorial. That's 5, 4, 3, 2, 1 over 2 times 1. Those cancel out. 5 times 4 is 20, times 3 is 60. There are 60 ways to do that, to have 5 people and pick 3 for positions. What about if there are only 3 people? 3 people. Well, that changes us all, right? To 3 and 3. And we get 3 times 2 times 1 on the top. 3 minus 3 is 0 factorial, but remember, by definition, 0 factorial is 1. So there are 6 ways. If I have 3 people, there are 6 ways to be able to pull this off, into how we could arrange them to be president, vice president, and a secretary. What if there were 2 people? Well, we run into some problems here. First, n is always supposed to be bigger or equal to r. So this has to be bigger than 3 or equal to 3. So mathematically, we can't do that. This is not possible. Second, from a practical point of view, I need to fill 3 positions, and I've only got 2 bodies for that. So we're not going to be able to fill all of them, and therefore we really can't solve this problem. So we can't do it with 2 people. We have to do 3 or more. For your summary, in problem 3, where did some of the factorials in the denominator come from?